Okay, we've worked out the size of an atom using quantum mechanics. Now let's use that to try and work out why matter has the density it does. To be specific, let's take, say, copper. Now, copper has an experimental density of 8960 kilograms per cubic meter, which is pretty high. Let's see if we can explain that. Now, first of all, we need to work out how much each atom of copper weighs. Now, if we look up in the periodic table, copper has an atomic number of 29, an atomic weight of 64. So this means it has 29 protons and 64 protons plus neutrons. Now, roughly speaking, a proton and a neutron have a mass, so a mass of a nucleon, that's been the collective term for protons and neutrons, is roughly the atomic mass unit U, which is 1.66 by 10 to the minus 27 kilograms. Now, in fact, neutrons weigh slightly more than protons, and how much an atom weighs also has to factor in the binding energy, and that little difference is the whole basis of nuclear energy. But for current purposes that doesn't matter. We can just say that a copper atom has a mass of about 64 atomic mass units, which is about 10 to the minus 25 kilograms. Not very heavy. You're not going to hurt your foot by dropping a copper atom on it. Okay, so that's one of them. But how many can we fit into a cubic meter of copper? Well, let's assume that the atoms are arranged in a rectangular grid. Something like this. Simply because it's simplest. In fact, they're not. They're in what's called a face-centered cubic array for copper. But it won't be that different. And what's the spacing here? Well, we weren't being too careful about how we defined the size of an atom, whether it was a radius or a diameter or anything like that. But let's assume that A was a radius. So that would be A, be another A over there. So we've got about a 2A spacing. I normally wouldn't worry about a factor of 2 like this, but it's going to be cubed. You're going to get a 2 here, a 2 there, a 2 there. And so when you cube a factor of 2, it's getting close to a factor of 10, which is worth worrying about. Anyway, let's assume it's that. So that means that the amount of space required for each atom is roughly a cube around it, which is going to be 2A on a side. So if A is about 10 to the minus 10 of a meter, like we worked out, that means the volume per atom is roughly going to be 2 by 10 to the minus 10 cubed, meters cubed. So we'd expect the density of copper be equal to the mass of each atom, 10 to the minus 25, times the number of atoms in a cubic meter. Now, if each atom has this volume, the number in a cubic meter is going to be 1 over that, which comes out as which is actually pretty good agreement. If you compare this up to here, that's within about 30% of each other, which for an integer calculation is extraordinarily good. So we can see why copper at least has the density it does. It's basically down to the mass of each atom, which is basically the mass of its protons and neutrons, because electrons are kind of irrelevant in mass stakes, they weigh so little. and the typical size of the atom, which is also technological applications. Can we actually make something that's vastly denser? But if you want to have a really high density, what we're going to need is atoms that are very close packed. So you'd want, we've said atoms are about 10 to the minus 10 in size, but that's not exactly equal for all atoms. Some might be a little closer together. So if you can find something that fits a little bit close together, that will help you. And you want each individual atom to be as heavy as possible, so have a high atomic mass. So indeed the densest things would be things like a depleted uranium, simply because uranium has such a high atomic mass and its size is about the same as other atoms. And it's indeed used, these ultra-dense materials, for things like the military, for artillery shells and better armour, because high density is often very useful. Now you may have heard that there are actually very, very much denser materials, like the material that makes up neutron stars and white dwarfs. We don't get them on Earth. How is that possible? We've seen that given the size of atoms and the atomic mass, we shouldn't be able to get density much above things like uranium. But in fact you can get a teaspoonful of white dwarf or neutron star material that weighs thousands of tons. What's going on here? Well, if you remember, we worked out the size of our atom by balancing two energy terms. We have balanced the electrostatic energy, which goes in, and the quantum mechanical energy, which goes out. We've got a minimum here, and that told us the size. But when you actually pack matter into something like a neutron star or a white dwarf, you have to add an extra gravity term, because gravity in these things is so intense, and that pushes the average size down. If you want full details, see the astronomy course. And so our calculation of the size of an atom doesn't apply in situations where there's an enormous gravitational force acting as well, in which case they can be very much smaller. And that indeed is what's happening to give the incredible densities you get in neutron star material or white dwarf material. But if you were to actually take some of this material away from the neutron star or white dwarf where the gravity wasn't that strong, it would probably expand back to more normal densities. So it's not something you could build armour out of, unless you could have some sort of strange force field to keep it contained. So we've seen there are good reasons why densities are typically of order for solids about 1,000 to 10,000 kilograms per meter cubed, and you're not going to be able to get something very drastically different from that.